picking up where we left off, of course, we're going to apply our integral formula for the fluid pressure right here. Um, so our example, find the fluid force in newtons this time. Water is 1,000 kilograms per meter cubed. And if we're working in metric, then we'll also note that gravity is 9.8 meters per second squared. So kind of coming at it from an angle, from a math angle versus a physics angle. I'm always going to provide you guys, with these sort of numbers. So I'll always tell you in a problem, in a quiz or a test, you know, what exactly these constants are. So water is 1,000 kilograms per meters cubed. And then I'll always remind you, if we're using metric, that gravity, we'll just use 9.8. Some people maybe prefer 9.81, a little bit more precise, but I'm just going to keep it simple at 9.8. And then that previous question you saw where we were using pounds, even in those, I'll always remind you that water is 62.5 pounds per cubic foot when we're using those units. Okay, so you need to see the drawing here. Let's try and keep these things on the screen. This is the beginning of the work. So this is what would be provided to you in a question there on the left, and we'll draw the connection, of course. So here we've got a plate. This plate is perfectly vertical. Okay, and we see the dimensions. So it's 3 meters here, 5 meters there, and the very top of it is 4 meters down, which is, again, this is quite a large plate and pretty deep down in the water, 4 meters. Okay. So how would you even begin? And the difficult part in these, of course, is just setting up the integral. Can we even set up the integral in the first place? That's really the challenge. And obviously that's what's new while we're learning this. Once we get to the integral, then it's a question of can we execute that integral. And at that point it might use one of our new techniques, or it might be something simpler. But the challenge is just getting there in the first place. Okay, so in a situation like this, here's what I recommend. Here's what I highly recommend. Set up your coordinate axes the way that I have, and I'll talk through it in detail. So we're making the surface of the liquid, here the water, the x-axis. Okay. So if I make the surface of the water the x-axis, and I'm going to say, you know what, this is a kind of a vertical edge, I'm going to make that the y-axis right there, running right along that edge. But notice something here that's a bit unusual. I'm making this the positive y-axis, not the negative y-axis. So y is increasing going down this way. And you see the little arrow. Why would you do that? Well, because that's how depth increases, right? As you go down, you get deeper. And so it makes sense to, as you go down, you're increasing your y value. Turns out that will make setting up the integral, in my opinion, a little bit easier. And it makes intuitive sense. All right, the deeper you go, right, you're increasing the y. So if this is the positive y-axis, well, then this would be positive 4. And another 3 meters would be positive 7. And we'll draw that triangle, and well, there's the 5 right there. It is possible to do these problems with the y-axis, drawn the normal way going up, in which case you'd have negative 4 and negative 7. But it's also good to practice, setting up your coordinate system a little bit differently. There's definitely a lot that your mind and your thinking will gain from switching things around a little bit and looking at it from a different point of view, even just from a mathematical standpoint. Okay, so what can we do with this? The first goal, I don't want to show you too much. if you think about our formula, right? So we've got, lots of parts. We've got rho, we've got a, b, d of y, and l of y. I find the most challenging of those by far is L of y, the length at any given depth. So let me go ahead and draw that on here. So at any given location on your plate, draw a horizontal line. That right there is L of y. And we can see, of course, that length changes as you get deeper. It gets shorter. To find L of y, how are we going to do it? Well, you see my hint there. Start by finding the equation of this line, and you're like, what is this line? Okay, so I'm going to draw it. So we need to know this angled line here. So I'm going to try and draw this kind of lightly. This line here, and we'll just extend that all the way through the x-axis like so. If we can find the equation of that line, then it's pretty much right there for us. What's the equation of that line right there? Okay, well, equation of a line, that won't be too bad. All we got to do is look at our drawing, and if we can identify the slope and the y-intercept, then we can get the equation of that line pretty fast. Well, let's think about it. Let's start with the slope. What is the slope of this line? And one thing to keep in mind here is your y-axis is now going positive this way. Okay, so when it comes to the slope of a line, we're just thinking rise over run, right? So maybe if you went from this point to this point, that makes sense, right? So what's the rise? You think, well, it went up 3. Ooh, actually no, because it's upside down, right? So it went down 3. The rise is -3. It went from 7 to 4, -3, but the run is still 5. So our slope, -3 over 5. If that's throwing you off a bit, you could always use the formula for slope, right? This is the point 0, 7. This is the point 5, 0, or excuse me, 5, 4. So you could use 0, 7 and 5, 4, y2 minus y1 over x2 minus x1, right? You could find the slope that way. And you'd find it to be -3 over 5. Okay, what is the y-intercept of this line? Well, that's a little bit easier. The y-intercept is +7. Okay, so there's the equation of our line. Y equals -3/5 x plus 7. Please ignore my work over here. We'll come back to that momentarily. Okay, so this is the way to begin, and we all but have it at this point. Problem is, like, why do we need to go any further? So L of y is with respect to y, and this is with respect to x. So we're just going to change things around. We're going to solve that for x. So let's see, solving for x, subtract 7, multiply by -5 over 3. I just did it in one step, but there you go. X equals -5 over 3 times y minus 7. So when we rethink that equation to be solved for x, that's it. We got it. That's L of y right there. L of y equals -5 over 3 times y minus 7. It's with respect to y, but it's really just the equation of that line. Okay, so at this point, some of you might be kind of scratching your heads, and you're thinking, okay, I see the equation of the line. I see we solved it for x, but I still don't connect it to why that would describe the length. So maybe I can help kind of connect the dots a little bit more. what is this equation here? When it's solved for y in the more familiar way, what is that equation really telling us? It's telling us wherever we choose to pick our x value, if we plug that x value in, that's the distance from the x-axis to the point on the line. So for instance, if we were to plug in 5, what would we get? Well, if we plug in 5, the 5's cancel, negative 3 plus 7 is 4. So at 5, the distance this direction is 4. All right, so if I go perpendicular to the x-axis, that length should be 4, the same number I get when I plug in. So this is telling us the same thing, but now coming off the y-axis. So if you tell me a y value, if I was to plug that in, well, that's how far I should come off this way. So let's say I was to plug in y equals 4. Okay, if I plug in y equals 4, let's see, that'd be negative 3, but then the 3's cancel, and I'd get 5. So putting in 4, that tells me to come out this way 5, and that's where the line is. So solving here, that's exactly what L of y is, right? It's coming off the y-axis out this way. It's that length, and it changes as we change our y value. Here's a good way to check your L of y, and this would be true in any problem we do here with fluid force. If you're not sure, if you're kind of in any level of doubt, even if you're not in doubt, it's still a good idea to check your L of y. So what did I do? I checked the endpoints, right? The 4 and the 7. Let's start with the 7. So if I put 7 in there, that should tell me the length at that location. Well, just from the drawing, what is the length of my plate at 7? You're like, well, it's 0, right? It's shrunk down to nothing. So if I plug in 7, I should get 0, right? It should tell me how long that plate is at that. Okay, well, when I plug in 7, guess what? I get 0. And let's check the other endpoint. Actually, we already did this. So when I plug in 4, it should match the drawing, right? At 4, it's got a length of 5. Well, when I plug in 4, negative 4 minus 7, negative 3, blah, 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 I get the 5. And so this, it's not checking every little point in between, but, I think it really confirms that we did this correctly. Okay, so we got L of y right there. What else? We need D of y, right? So we got L of y, we're off to a great start. D of y. Now this is D of y. Now at this point it's really helpful that we drew our y-axis going down this way. D of y, you might say it's so simple it's confusing. D of y is simply y, the way we've set up our xy plane. If I was to draw D of y here on our graph, there's D of y right there. It's the depth at that same length. So I want it to stop where I drew my line. Okay. So we're imagining it's the same y value, right? And there's the length of that y value and there's the depth of that y value. So why would D of y just equal y? Well, if we're thinking, at any given y value, well, whatever y value you're at, that's the depth. That's how we drew this in the first place. So if I was at 4, then the depth would be 4. If I was at 7, then the depth would be 7. Okay, it would always equal. With that, kind of try and keep some of this sort of on the screen. We can set up our integral. All right. Now it'd be a lot better if we could kind of talk through this piece by piece, especially these first couple parts, if we were in class together, but we're not. Okay, so the fluid force, remember it begins with rho. right? The density. Okay, so when you're dealing with metric, and when they tell you, water is 1,000 kilograms per meter cubed, grams and kilograms, they don't take gravity into account. You're probably maybe familiar with this by now. So to get rho, we can't just put in the one number 1,000. We need to multiply that by gravity, the acceleration due to gravity. So our density here is 1,000 times 9.8. Okay, we don't have to do that when we're working with pounds because that already takes gravity into consideration. All right, so there's our density, 1,000 times 9.8. What's up with this integral from 4 to 7? Okay, let's go back to the drawing. We begin at a depth of 4. We end at a depth of 7. There you go. Integral from 4 to 7. And then we're plugging in our d of y and our L of y. So for us, y times negative 5 over 3, y minus 7, and we integrate with respect to y. Okay. So a lot of work and a lot of thinking just to get the integral. Well, that makes sense. I mean, that's what's new about this material and the application, right? Just setting it up. Now let's see, can we execute? This one's not going to be bad at all, right? We can multiply these numbers. We can even pull out the negative 5/3, and we'll see this. Okay, so those two numbers together and the negative 5/3. So that would give me negative 49,000 over 3. Integral 4 to 7. And what do we do? Well, let's just distribute the y. So y squared minus 7y. And this is going to be very straightforward. We just got a polynomial to integrate. So let's just wrap this one up. And it's very fast once we have this, right? Negative 49,000 over 3. And then 1/3 y to the third minus 7 over 2 y squared. Integrate from 4 to 7. And I'll just kind of show you the rest. Turns out the answer is a whole number. It turns out really nice. Plugging in the 7 to that whole thing gives you negative 343 over 6. Subtract, plug in the 4 to that whole thing, negative 104 over 3. And you would really expect a fraction as your answer, but no, it turns out when you do all that calculation, 367,500, and the units here is newtons, which we use a capital N. Okay. So there you go. Let's stop this video.